Hello everyone, welcome back to my YouTube channel. In this video, we are going to discuss dimension reduction techniques. We will delve into the realms of dimension reduction techniques, specifically focusing on the concept of multicollinearity and its implications in data analysis. We'll explore the importance of understanding and addressing multicollinearity, a key challenge often encountered in statistical modeling. We will then embark on a journey into principal component analysis, a powerful technique for reducing the dimensionality of data while retaining as much as information as possible. Finally, we will delve into the practical application of PCA in real world scenarios and learn how to implement it using Python. Multicollinearity, and when is multicollinearity not a problem? Multicollinearity occurs when two or more independent variables in a regression model are highly correlated. This can lead to unreliable and unstable regression coefficients, making it difficult to interpret the impact of individual variables on dependent variables. When it is not a problem, multicollinearity is not always a problem, especially if you are not interested in interpreting the individual effects of the correlated variables. If your primary focus is on prediction rather than inference, multicollinearity may not significantly impact the model's accuracy. Identifying multicollinearity using variance inflation factors. What is variance inflation factor? It is a common metric used to assess multicollinearity. It measures the extent to which the variance of regression coefficient is inflated due to the presence of correlated predictors. Its interpretation is a VIF value of 1 indicates no multicollinearity, while the values greater than 5 or 10 suggest a moderate to high level of multicollinearity. This suggests that the model is not robust and the coefficients may be unstable. Now we will move on to principal component analysis. In this topic, there are two subtopics, that is data transformation and variance. In principal component analysis, uh, it is a statistical technique that transforms a set of correlated variables into a set of uncorrelated variables called principal component. It essentially reduces the dimensionality of data by finding the directions of maximum variance. In the variance, each principal component captures a certain amount of variance in the original data. The first component captures the most variance, followed by the second, and so on. By selecting a subset of principal components, we can retain a significant proportion of the original information while reducing dimensionality. Applications of principal component analysis. Consider a dataset containing information about customer demographics, purchase history, and website interactions. PCA can be applied to reduce the dimensionality of this data by combining correlated variables into principal components. This can help identify customer segments based on their behavior and preferences, leading to more targeted marketing campaigns and improved customer experiences. PCA can also be used to identify key features key factors driving customer satisfaction or churn, enabling businesses to focus their efforts on improving these areas. How many components should we extract? It is dependent on the eigenvalue criteria, proportion of variance, and third is scree plot. So we will discuss the eigenvalue criteria. What are eigenvalues? Eigenvalues are scalars that indicate how much a vector is stretched or compressed during a linear transformation. What is threshold? The eigenvalue criteria suggests retaining components with eigenvalues greater than 1. This threshold indicates that component explains more variance than a single original variable. The higher the eigenvalue, the more variance is captured by the component. The proportion of variance explained criteria. Cumulative variance. It represents the proportion of total variance captured by a set of principal components in dimensionality reduction. Target. This criteria aims to retain a sufficient proportion of the original variance. For example, we might aim to retain at least 80% of variance, which would indicate that the selected components capture the majority of the information in the original dataset. Validation of principal components. Validation of principal components involves assessing their ability to explain variance in the dataset effectively while avoiding overfitting. Techniques like cross-validation, explained variance ratio, or reconstruction error are commonly used to ensure that the selected components generalize well to new data. Here is a small code estimate to perform principal component analysis using Python. You can pause the video and read out for yourself.